have been great for us. They've been really exciting, and of course we know why, because on Saturday, after 7 months, we have been receiving the first 300 data packages from Philae, exactly at 28 minutes past 10 in the night. And since then we have been really busy analyzing those data, trying to find out what we're going to do with Philae and with Rosetta. So let me introduce the panel to you. On my very left and to your right is Professor Mark McCaughrean. He is the Senior Science Advisor at the European Space Agency. Then next to him is Elsa Montaron, and she is the Deputy Flight Director of Rosetta at the European Space Agency. And next to her is sitting Barbara Cozzoni, and she is from the PLR Lander Control Center in Cologne. And then we have Philippe Goudon. He is the Philae project manager of the French Space Agency CNES. And left to myself is Professor Jean-Pierre Diebling. He is the lead scientist on the Philae lander. And with this panel, I think we have really all those experts you want to have on our panel to tell us what happened in the last few days and what's going to happen, of course, even more important, in the next few days. And with this, I'd like to give the floor to Professor Mark McCaughrean.
Good morning, everybody. It's a huge pleasure, as Marcus said, to be here on a very interesting day, just a few days after the lander Philae has woken up. And the panel will talk a lot about that this morning, but I'm going to try to set the scene a little bit and introduce you to the mission Rosetta, just to tell you where we are. Of course, Rosetta and Philae are at a comet called 67P Churyumov-Gerasimenko. But why are we studying comets at all? They're these fascinating objects in the night sky that appear seemingly randomly over history. They're beautiful objects which are there, but for scientists they're more than just beautiful, of course. They are treasure chests of information locked up from the birth of the solar system 4.6 billion years ago. They are products of the birth and evolution and death of other stars. They have locked up material which didn't find its way into our planets, but can provide clues about the origin of the Earth, the origin of its water, and even the origins of life on the Earth. So studying comets in detail is of enormous scientific interest, but of course they are fascinating objects to explore just for themselves. In 1986, of course, the European Space Agency was the first to fly past a comet with the Giotto mission, and that comet, of course, was Comet Halley. This was a brief encounter at 68 kilometers per second, so it lasted only minutes. And one of the ambitions, even at that point, was immediately to say, well, how do we really understand a comet? To do that, we want to rendezvous with a comet, live alongside it all the way through its passage towards the sun and back out into the cold of deep space again. And with that in mind, the Rosetta mission was proposed, designed, and built. This is just one view of Rosetta. This is one of the very long solar panel arms, or the solar arrays. Rosetta is a huge spacecraft, 32 meters across, and able to operate out in deep space on solar power alone. And here's the spacecraft itself, and here you can see the Rosetta main spacecraft at launch, 3 tons, with Philae, 100 kilos, on the side. The comet that we're at today, and which we got to over a 10-year journey, is again 67 PCG. It has a 6.5-year period around the sun. It goes out beyond Jupiter and in at its closest point to the sun between Mars and the Earth. It doesn't go so close to the sun that it will be destroyed. Nothing on the 13th of August will happen of that kind. But it's an object which changes enormously in the amount of sunlight it receives, and therefore its activity changes. But you can't get to a comet like this simply by firing a rocket into space. You can't rendezvous with a comet on an elliptical orbit. So we actually had to fly past the Earth 3 times and past Mars once in order to use the gravitational pull of those planets to get us onto the correct elliptical orbit. By the time that we were actually out towards Jupiter, lining up to get behind the comet, we actually didn't have quite enough power to run the spacecraft safely, so we went into hibernation with Rosetta for 2.5 years, until we arrived at the point, January the 20th last year, when we received the first signal as Rosetta came out of hibernation. And you've seen all of these pictures before. At that point, there was huge excitement, of course, because we now had a mission. It seems like a long time ago, but it's less than 1.5 years ago that this moment happened. How to study an object like this? This is 4 kilometers across. It looks like it's made of rock, but we now know that it has a density less than that of water, half the density of water. It's a mixture of ice and dust and complex molecules, carbon-bearing molecules, and a completely bizarre landscape in which we see boulders sitting on the surface at apparently bizarre angles. We see plains of dust and rivulets of material. And this is a comet which is not active at this point. And we expect and we see that the comet is changing dramatically as we watch it now as it begins to approach the sun. And just one example, this is my favorite point on the comet, is this fantastic landscape where if we pan up here, you see a cliff that is 100 meters high. And you know, immediately those of you who have fun in your life at the weekends would think base jumping here, right? You would go, you know, you'd want to jump off the top of this cliff. Well, it wouldn't be very exciting because it would take you 20 minutes to get from the top to the bottom. The gravity of the comet is so weak. And in fact, you'd have to be careful because if you actually took a jump at the beginning, you would fly off the comet rather than just fall to the bottom. But the upside is you wouldn't need a parachute because you could just end at the bottom and you would walk off the base jump. There is, of course, this picture, which the less said about, the better, but it has captured the public's imagination, this object. And so somebody made this, you know, maybe there's a ski resort on 67p. But again, the level of exploration that people have witnessed with this constantly bizarre object has engaged the world, and it's something which has been exciting for us to be involved in, but of course that we're there for science. And this shows you, and I won't go through this in detail, I'm sure that my colleagues here will give you a bit more description, certainly about what we have on the lander. We have a whole array of very sophisticated scientific instruments on both Rosetta, the orbiter, and on Philae, the lander, which lets us not just take pictures, but study the material properties of the comet, understand its evolution as it moves closer to the sun, and the environment around it, because comets, of course, have their tails as materials stream away. So we have this very sophisticated set of instrumentation, and scientific results have been pouring back from Rosetta, some from Philae during its period in November, but we hope to have much more, of course, now with Philae alive. And that's the real story. That's why we're there, is to do science. And the scientific results that we're seeing, I have no time this morning to give you a full view. We have various geographical regions on the comet which have been labeled with an Egyptian theme following Rosetta, the Rosetta Stone. We have these bizarre pits. These are not, they're craters, but they're not impact craters from the outside. They're places where material streams out from the inside when the comet warms up. And we see this strange structure inside those pits, as if this is a clue about what the comet's made of on the inside. Because what we see on the surface is covered in dust, but the inside material, the mixture of ice, other volatile materials, dust, and complex molecules is what fundamentally we're interested in. And these pits are alive. This is one of those pits again, and if you increase the contrast, we see material flowing out. So this is not a dead body at all, and in fact, in recent weeks, this image from the OSIRIS camera on Rosetta has shown this fantastic jets which are emerging even in the darkness. These are after sunset on the comet. The comet turns every 12.5 hours. There's enough heat now in the comet to have jets of material flowing out even when it's dark. We capture dust from the comet. We analyze those particles to see what the comet's made out. We capture gas. We try to understand the isotopic ratios, how much of this material versus that material, to understand what the comet's made of. And we understand the environment of the comet to the extent that we can measure how that material streams up against the wind coming from the sun. And you can even hear the comet. If I just play the sound of the comet from its magnetic field data. This is not what humans would hear, of course, it's what scientists have made of it, but again, it captures the imagination that you can somehow hear a comet in space. And of course then we came to November and the point of landing Philae, and again my colleagues will talk in much more detail, but let me take you briefly through that. We had to find a location on the comet that was 1 kilometer across and relatively clear so that we could touch down, because we were not guided onto the surface, we were throwing a dart onto the surface. This is the place we chose, the 1 kilometer circle, the site called Agilkia. And you can see where the touchdown point was hoped to be in the middle there. This is Philae departing from Rosetta, the orbiter, descending down towards the surface And this is the view from Philae itself, approaching from about 40 meters down to just 10. And you see the structure, the surface that we landed on. If I now, as a simulation, this isn't a real picture, if I now put Philae to scale in that picture, this is where Philae touched down. And you can see it's not a smooth surface. And as you know, the harpoons didn't fire, we did not secure it to the surface, we left that point and went elsewhere. Of course, there was jubilation at being the first people ever to land on a comet, an enormous success. And this is the point that we touched down. You can see the point where we touched down. Here are the 3 feet in the imprint made in the dust, and we can actually even hear the touchdown simultaneous with the mobile phone. There was no mobile phone signal, but that was the sound of touchdown on the comet. But of course, that was a bounce. It wasn't a secure touchdown. And we saw, only minutes later, Philae leaving the scene of the crime. Of course, and Jean-Pierre will talk in detail about this, this is one of the iconic pictures from the mission, the first picture from the surface of the comet, and I leave to Jean-Pierre to talk about that. What we have reconstructed is where Philae first touched down, the red dot in the top left corner, and the second dot, a little lower down, is where we bounced, we hit a cliff, and we ended up somewhere, we believe, in this ellipse. We have located Philae to a region about 160 kilometers by 16. Somewhere in that area is the lander. We now know that it's in that area from the data we've got in the last few days. So let me conclude by saying that this extraordinary journey is by no means over. We are not at a dead object. We are at a living, breathing dragon of a comet, which is coming to life as we come close to the sun. These are pictures taken back in March, January to March. This is the amazing place that we are. This is the place we're exploring. And just to finish, today the lander is alive, but Rosetta has been there doing science, and together again they'll be able to do stunning new science, and we will carry on through the perihelion point on the 13th of August, the closest point to the sun. We're currently funded to run the mission until the end of this year, but we have proposed to, internally within ESA and our funding body, that we will then run the mission through to September next year. And what we aim to do in September next year is spiral Rosetta slowly down to land on the comet as well. And that will be the end of the mission. There will be no operations after that, but I think it will be a fitting end to an astonishing journey. And for those of you who are social media savvy, we have a huge amount of information that you can follow along with. All I can say today is just another point in this journey, and it is to be continued. Thank you.
This introduction, and now we're coming to those who actually fly the spacecraft, and I mean in plural because we have Rosetta and we have Philae. And the next speaker is Elsa Monteron, and basically she is the one to blame that all this happened, because in the very night when she had to decide whether it's time to separate the 2 spacecraft, she was the one to say, yes, we are going. And with this introduction, I need to go to you, Elsa.
Thank you very much. Good morning, everybody. It's a pleasure to be here with you this morning. So I'm going to talk about the operational challenges of the Rosetta mission operations. So I talk from the ESOP side about the Rosetta orbital operations, and my colleague Barbara will talk then about the lander Philae operations in more detail. So indeed, Marcus asked me to bring you back to the night of before the 12th of November. When I started my shift on that night, I can tell you things were looking very interesting and not quite as expected as we thought. But then luckily, thanks to the work pulled by all the teams throughout the night, in a few hours, we were able to declare the go of the various elements for separation and landing, with the go of the Philae about an hour later than expected, but still in time to make separation. From that moment, things went much smoother than they had been before. And as Mark said, we finally had a successful touchdown, only 120 meters away from the point we're targeted, which for me is still an amazing achievement, which is a highlight of a series of challenges I don't want to mention all of them to you, but let's just say that in that year, we had successfully woken up from hibernation, rendezvoused with the comet, orbited it, characterized it within a few weeks and months, and finally safely landed a robot on it. This was an amazing year. Now, Philae, facetious as ever, decided not to stay there, as we all know. So this is another view Mark showed you before, where the touchdown point, the lander was observed from the Rosetta orbiter using the cameras we have there. So we have a last observed point from there, and then there is an area where we think it has landed, and my colleagues will talk more about where it could be. What happened after that? I mean, Rosetta went, after this world exciting events, we continued, of course, the focus going more onto the scientific mission of the Rosetta orbiter spacecraft. So after the lander delivery, we had a series of maneuvers to bring us into the Terminator plane, which is a plane going through the comet perpendicular to the Sun. It's a plane that is safe to fly the orbiter because it doesn't have eclipses, and in terms of comet activity, it's also a good place to be. So for several months, we actually stayed in that plane and brought the orbiter to a distance to the comet of about 20 kilometers. And since we're very stable there, we could do a lot of science at that point. We stayed in this type of circular bound orbits around the comet until roughly the end of January. During this period, our colleagues used the orbits we were on to keep searching for Philae. So on the sequence of commands which was loaded on board the orbiter, there were picture-taking commands to try to locate visually Philae on the surface, and my colleague will talk about that, about the candidates, landers we found in this process. Then, after the end of January, we decided to change the trajectory approach, and we went into escape trajectory. So not anymore bound orbits around the comet, but more something that looks like this, which looks a bit science fiction. It's not orbits in the classical sense. They are basically arcs which are flown, and then at each spike of these points, we do a maneuver to basically bring us back closer to the comet. We started flying this pattern. The idea was to give us more illumination, different illumination observation conditions on the lander, to explore also further away, which for certain instruments is favorable. And we basically regularly came back closer to the lander, to the comet, with an altitude of typically several tens of kilometers, 70, 50, something like that. The plan was also to do close flybys. So on mid-February, on the 14th of February, we had the first such close flyby with an altitude of only 8 kilometers above the surface. And then towards the end of March, we had another one at 15 kilometers. I will talk more about these flybys because actually the comet started to be active as we come closer to the Sun. And as we flew so close to the comet, we had done that prior to the lander delivery, but this time, with the comet active, the orbiter started to behave in a different way. I'll talk about that in a second. To give you an impression, this is a plot of the comet distance. It starts on the 12th of November, so the date of the Philae landing. You see there that we are at distances of a few tens of kilometers, 20, 30. As I mentioned, until the end of January, we stayed in that region with bound orbits, and after that, you see that the distance is evolving with points that come much closer for the close flybys. During the flyby at the end of March, as I said, we had basically the Rosetta spacecraft enter safe mode due to the dust that was in the environment of the comet that gave problems to the orbiter to track the stars. And after this event, it was decided to retreat and go to a higher distance. So at that point, we flew still these escape orbits, coming close to distances of roughly 100, 125 kilometers, and staying below 180 kilometers generally. But then we had another event with the star tracker. We saw that the comet activity was affecting the orbital operations even more. So since the 24th of May, the operations team decided to retreat even further and stay in a domain between 200 and 240 kilometers from the comet. Since we had the Philae signal over the weekend, on Monday morning there was a meeting to discuss how to continue with the trajectory. And we have decided that based on the observations we have made in the last weeks, it was safer to come a little bit closer, so Rosetta has been maneuvered now to come down again 280 kilometers, which we reckon should be safe. But as soon as we see activity coming back, we may have to retreat further. I will talk more into detail about this issue in a second. So listening for Philae, this has of course been a topic since months. You probably know that Philae communicates with the Earth via the Rosetta orbiter. It has an interface box onto the Rosetta orbiter. After the lander delivery, the lander control center in Cologne asked us to switch off this interface box. If the box is switched off, there is no signal that will be received, it's clear. But since the 12th of March, there have been campaigns to switch on this unit. And as soon as the unit is on, if the lander detects the signal, it will forward its telemetry back. So we went through 3 such campaigns without a signal being received, and finally last weekend, just in time for today's event, Philae finally came back. We had, as Marcus mentioned, 85 seconds of stable RF contact with Philae on the night of the 13th of June, and then 2 comet revolutions later, another series of signals, 3 times 10 seconds of a stable signal. So as I mentioned, the key here is to maximize the communication with Philae. It's of utmost importance at the moment, and see whether we can get a stable communication pattern between the 2 machines. Because if we can do that, then we can do the next step and resume the scientific operation of Philae. So the mission control team has been meeting on Monday and has decided to optimize the trajectory to stay around this zone where we have had the first contacts, optimizing the flight profile of Rosetta to try to maximize them as much as we can, compromising on the distance due to the dust effects on the Rosetta orbiter. And this is the point, basically. You've seen these pictures in Mark's presentation. This is what it means to fly in the dust. The comet is a very, very active object at the moment. Imagine taking your car through a snowstorm. You don't see very much. It's not very safe. Well, there it's comparable. The comet spits out elements which can be extremely bright. Generally, it also increases the background noise on the sensors of the units we use to track the stars, which the spacecraft needs for its operation. I show you here a graph that on the bottom you have the sun distance. So you have to read it a bit unconventionally from the right to the left. The sun distance is computed, basically shown from the moment we arrived at the comet last August until now. So you see that during that period we went from a sun distance of 3.6 AU, the distance between Earth and Sun, down to roughly 1.6 at the moment. So it's a tremendous range. In red, you have the comet distance we were at this moment. And there, the curve is not very accurate. It's basically 1 point per month, just to give an idea. As you can see, on the right-hand side, we were at the beginning coming closer to characterize the comet. Then we came as low as a few tens of kilometers for the landing and stayed there until end of January, as I mentioned. You can see that at period, the blue curve stays very close to 0. The blue curve is giving us an indication of the loss of track events on the star trackers of the Rosetta orbiter that we need for the spacecraft to determine autonomously its attitude, its orientation. And you can see that then, from a point at 2.5 AU from the Sun, suddenly the blue curve starts to pick up. And you can see that at that point is about the time where we did the close flyby at 8 kilometers and then the close flyby at 15. And this is where we started to see the effect of the dust on the Rosetta orbiter. Then, as we said, we retreated to higher distances, so a range of hundreds of kilometers and then 200. But you can still see that at these distances, as we come closer to the Sun, the number of star tracker events is still observed to be increasing. Just to give you a feeling of what we're talking about, I put here these 2 images. They look very similar, right? I mean, these are images of the star tracker sensor. They are pictures of what the star tracker is seeing. You can see a lot of bright points on there. Some are stars, but many of them are dust. Generally, the amount of noise on this sensor is increased in the dust environment, but the problem is that some of these bright objects are also dust, not stars. Some of them, you can see the lines, they are moving very slowly. On the right-hand side is also a picture of the CCD of the star tracker. Now, the difference between these 2 pictures is, on the left-hand side, it's a picture taken by the Rosetta orbiter in April. It's taken at a sun distance of 1.7 AU and a comet distance of 95 kilometers. The right-hand side is a simulation from '99 done by industry to simulate the effect on the star tracker of an active comet environment. As you can see, the two look very similar. The star tracker is behaving as expected. We are not dealing with an anomaly here. The simulation was done for a sun distance of just above 1 AU and a comet distance of 4 kilometers. What this is telling us is that we were expecting in a dust environment that we would have to back off. We knew that the star trackers would have difficulties tracking. The thing is, the comet is very active, so we may be seeing this maybe a bit earlier than some people would have hoped to see. But the reality is, we have to deal with it now. And the only way, also defined by industry at the time, is to stay safe and retreat to a distance where these effects are not encountered. The effect of this is basically not only the star tracker may lose track, it's designed to reacquire track very quickly, but if it fails to do so within a certain amount of time, then it will do a so-called lost in space acquisition. There it takes a wider image and tries to map the stars. If it finds objects that look like stars, it might identify them in its catalog, believe that they are stars. The objects are moving, so it will move with them, and then it will depoint from where it should be. And then the autonomy catches it and reconfigures, reacts. If this happens too often, then the Rosetta orbiter goes into safe mode. So it's really a safety critical situation, which is the reason why we have to stay away. So basically, the next milestone is on the 13th of August, we have perihelion. We do expect that until then, the comet activity will increase. So this situation will continue for the months to come. And then we will go further away from the sun, and then the comet activity will decrease, and we will eventually go back to the situation we had at the beginning, where flight was extremely smooth and we didn't have these effects. As Mark said, at the end of the year, we have the formal end of mission, but we know that we have enough resources to continue until at least September, so we look forward to that, to be approved. And with this, I would like to thank you.
So, to put a little bit more clarity, ELSA is the spacecraft, let's say, driver for Rosetta. And then we have Barbara from DLR, and she is dealing with Philae, with the spacecraft itself, and then there is Philip from CNES, and he's dealing with this, what we call science operations. So he is basically really programming, helping to work the instruments on the lander. So that's a little bit the three roles of the two ladies and Philippe. And even more important, right, here to my left is Jean-Pierre, and he's talking about science. Because in the end, why do we do this mission? Because we want to find out interesting things. For example, where the water came from on Earth, or are the building blocks of life also coming from comets? So that's then about science. And with this little entertainment in between, I hope you've been switching to the next presentation. And as I said, it's Barbara Cozzoni. She is working in the DLR Lander Control Center in Cologne, and she is, if you like,
that the lander did not switch on the 13th of June when we had the first contact. Analyses are ongoing to understand, to try to recalculate the exact switch on wake up of Philae, which is probably days before. So, what we got from Philae? Only good news. So, DPU, both DPUs are working. This means that we have an onboard computer fully redundant. We have much more data waiting for us on the mass memory. They are full, so hopefully with the next communication we'll get more data, more information. We have a software which is performing very well, is actually able to detect the day-night cycle on the comet. I will explain later why this is important for us. We have seen that the lander internal temperature is very good. The lander is warm. This is the telemetry we got for the only full comet day we have at the moment. And you see that at the sunrise, the temperature is already -36, which is great. The minimal operational lander temperature for the lander is -45. So we don't need any warm-up strategy. We can start straight away in the morning to operate the lander. And another very good news, our solar panels, they are collecting energy. We have 4 solar panels, 1, 2, 3, and 6, the one on the top. they don't look so much covered by dust because they are performing as expected. So, looks like Philae is ready for operation now. But first of all, we need much more telemetry. It's too early. So we need more data to assess more specifically the status of the lander and to better understand also the condition on the comet, day-night cycle duration and power we get. And much more important, we need the help for Rosetta. We need longer and stable RF link predicted also. We need to know when the link is now, when we have a link now, we need to know when is the next link. Only knowing this, we can plan our activity. So let's talk now about our strategy for the long-term science. Long-term science is the science we are starting to do hopefully soon in the next days, weeks, and so on. So we want to prepare and upload activity as a chain of sequentially and autonomously executed slot. One slot is 1 day. So the activity inside this slot, the slot depends on few factors. The power and the data budget we have for that day, the Rosetta communication link, and in case also we have to take in account if we want or not to recharge the battery, because for certain operation we cannot use only the power from the solar panels. For drilling and analyzing the sample from the terrain, we do need the support of the secondary battery. Here you have a plot of, let's say, an example of a comet day. You see basically at the sunrise, the power collected from the solar rays start to increase. At a certain level, we will have the lander boot. We need to wait a bit longer to have enough power to start our operation, our science. And then that's why we need more information. We need to know how long is the day to schedule accordingly the activity. At a certain point, this is the good news for us, the software will recognize that the night is coming because the power is decreasing and it's already working, we have seen that. So it will stop the operation, it will copy all the data collected in the EEPROM, so we don't lose anything at the switch off, and it will basically tell Philae what to execute the day after. We do not necessarily need a link every comet day. When we know exactly when the links are, and once we know how many packets, how much data is generated, and the capacity of our mass memory, we can plan basically all the operation for few comets day, add a link at the very end, and download everything. So, in the meantime, in the last 7 months, we were not just praying for the lander being back, we worked a lot, so we have some operation ready. We will start with what we call low cost, low risk, obviously. So the first block, for example, is Sesame, Romap, and Mupus. So we will start with all the operation we do not require much power and no mechanical movement of the lander. Then, okay, we will start with some more demanding concept, Shiva and Rollies, to have a picture of the surrounding, Sesame, and so on. Philippe will give a presentation more in detail of that. So we start with something simple, not demanding too much power. Then, with the time evaluating the results from the first operation, we will decide to go on with more complex, more power demanding and more risky operation. So we are preparing, we had from our science community the priority in which science to execute. We already test many of these operations, they are ready, but for the execution we want to wait and see what how Philae is performing. Obviously, we also ad hoc, according to what we will see, we will also add some slots dedicated for the battery recharge, the secondary battery. As I said, for some operations we do need the support of the battery, and there will be some slots for eventually moving the lander, rotation, lifting, lowering, according to the mechanical operation we have to perform. So, That's it. Philae is back, and we are all very happy. Thanks.
Thank you very much, Barbara. I mean, it is back. That's the news, that we have all been waiting for. And the more Philae is back, meaning that the power situation is stabilized, the more happy Philippe will get, because then he's finally able to command instruments on. And as we just heard, there will be a certain strategy, but what I was again already spotting immediately, there will be new images, because of course illumination is changing. So what we saw already during landing, we might get new things. And with this, I need to go to Philippe to explain what is the strategy behind the sequence of instrument operations.
Thank you. Good morning, everybody. I will start by presenting to you what we did in November to recall everybody what we succeed to do. So this part was called the first science sequence, 2.5 days of science operation were done. There is a short movie here showing you what, not the right order, what we should have done if we would have landed on Agilca. So we would have started by the Shiva images all around the lander. And we have here with us the PI of Shiva, and we will show us the result. After that, we would have done release images under the lander. You can see that the platform can rotate, so that we can do a drill at one point. We would have retrieved a sample, analyze it with Cossack and Ptolemy. We can move again the lander and put the mucus hammer on the soil of the comet. This hammer vibrates and enters the soil to measure the strength of the soil. After the deployment of the APXS instrument under the lander to measure the contents of the soil in terms of atoms. And finally, this movie doesn't show it, but we can use also the concert antenna. So it was a theory, but unfortunately, as you know, we did rebounds and we didn't arrive at the Agilca place, but at the Abydos place. It's the name we gave to this place. And we landed, but more on the side, and of course you know that it has not anchored. So taking into account all these, we have been obliged, we were obliged to change the scheduling of the operation. Moreover, the day-night cycle was not the same. The communication link between the lander and the orbiter was changed. So we were obliged to change the way to do the operations. So the first part that is called on your left SDS, separation, descent, landing, and block 1 was not changed because it was inside the software and we couldn't change it even if we didn't land on the right place. So it was done and we succeeded to do science even during the rebounds, thanks to this. And after, we took a certain time to think what to do, and we changed from this point the scheduling. We decided to do safe blocks. That means to do from the less risky to the most risky, to operate instruments that don't move. So it was the case of OMAP, mucus, sniffing mode of Cossack and Ptolemy, and and the CISA. And after that part, we decided to take more risk. So we deployed the mucus instrument, and we deployed in parallel the APXS instrument, what you see on your right here. And at the end, seeing that all was okay after this deployment, we decided to do the drill. It's the blue part here, the SD drill operation. And unfortunately, as you know, we didn't succeed to take a sample of the soil because of this not optimized situation of the soil. Finally, we did release images, a series of release images, and we rotate the lander, we optimize the rotation of the lander to have maximum illumination on the solar panels. And the last science operation was the concert operation, concert measurement. So to summarize, what we did in November is the fact that 8 instruments succeeded to do normal science. The green flag you see here, all these instruments retrieve data and succeeded to do science, and Jean-Pierre will show you, will tell you what are the results. Unfortunately, SD2, the drilling system, didn't take a sample, and APXS didn't touch the soil. So it's something we think we will be able to do during the LTS. I will come back later on this. So to summarize, we consider that we have achieved 80% of what we intended to do during the LTS. So since November, we knew that the situation has improved. And what we did is the search for the Philae location. We were lucky because first, just after the touchdown, Osiris succeeded to take a picture when the lander was flying during the rebound. So we knew the direction. And with other instruments like Mutus or Romat, we succeeded to know when each time the lander touched the soil. And finally, we saw that we went above this big crater and fall between boulders close to the cliff. So we succeeded to find a close location, 50 meters large, maybe, yes, it's visible here, the blue circle in which the lander should be. And moreover, very recently, the Laboratoire Astrophysique of Marseille seems to have found the lander here on these images, comparing different images before and after the landing. It's not 100% sure, of course. We should have a new close flyby to be sure that it's the lander. But what we can say today is that the last data we have received are compatible with this location. Here, a picture to show you also the different field of view, and that, but I think Jean-Pierre will come back and explain more on this point later. The big difference between Aegyptia and Abydos is we should have landed on the northern hemisphere with 9 hours of day for a rotation of a comet of 12.4 hours. And here we are in the southern hemisphere, so during the winter. So it's the only curves I will show you, but it's the improvement, the comparison between November, it's the ratio 1 at your left, and what we can expect in the best time in August. So the current situation is the black line, vertical black line here, you see that, for example, because the comet has come closer to the Sun, we have gained at least a factor of 4 in terms of energy on the solar panels. And we can expect with the blue curve also a longer day duration. And we have two dotted, blue dotted lines. The first one on your left is the equinox, and on the right, the one on the right is the solstice, the summer solstice. So you see that the best time for the lander would be August, because during August we will be close to the Sun and the duration of the day will be the best for us. So the situation is improving, and we were waiting for the wake up, of course, and it's good luck that it happened last weekend. So I will finish my presentation by the long-term science. Just we have discussed a lot this during the last months. It's again or still TPC, TBD, and to be discussed with our scientists. But the rationale should be what Barbara you explained. Start by the less risky to go to the most risky. So we will start by doing certainly ROMAP measurements, mucus measurements, and sesame measurements. It's they are small consumers, only a few watts, and they don't require movement. After that, we would do Shiva and Rollis images. We would use concerts. We would also use COSAC and Ptolemy, the two analyzers, clinical analyzers, but for using them by sniffing again the outgassing of the comet and the dust of the comet. And the last activity should be the most risky. That means to do a second deployment of PXS, so that after rotation of the lander, to optimize the distance between the platform and the soil, we should be able with a PXS to touch the soil, and we should be able with SD2 to take a sample, to retrieve this sample, to show this sample, to see this sample with Shiva M, and also to analyze this sample with COSAC and Ptolemy. So it's something we will do, maybe not in the next week, but certainly next month. That's it for me. And maybe ready for any questions later.
Good morning, everyone. More than moved and glad to be here today, of course, as you can imagine. You will note in every one slide there are a few days which count more than the others and are exactly there with that mission. And my very first words would be to thank all those who make us enabling doing that. And of course, ESA is at the very core of that. I remember what Roger Bonnet did in the 80s, 90s to let us have this mission here, and Jean-Jacques Dordain, who was very close by here, also is someone who really always had science in his heart. So, of course, we are the scientists very knowledgeable of what has been done for us to be here. We are absolutely convinced that, you know, the space exploration of the solar system goes by step. And actually, although it started a few decades ago, we are still at the very first round of that. And I'm absolutely convinced that Rosetta in the future will count as one of the major steps understanding where we are, why we are here. And again, we are now with the space exploration in a real revolution of our understanding of what the Earth looks like and why it's in here. And Rosetta is one of the stones that really enabled her to build that here. So, big thanks there. Just a reminder that Philae started not as a system or an instrument made by ESA, but an instrument with an AO actually, and Philae was the number 11 instrument to be asked for, and actually we responded at that time, and Philae is really something that was conceived as to be launched by ESA, to be there as the other instruments, that for a reason that I'm not going to elaborate here, finally we merged two different concepts into one, which became Philae. On Philae, we had to build not only the system but the instrument, because that was really done for that, and we have 10 instruments on board. So we have as many instruments on Philae that we have globally on Rosetta, but of course we interact very strongly. Operation-wise, you have heard what it is, and now I will really let you know what we did on science, but we've got to realize that it's been developed in a very highly integrated pattern between system and engineers and scientists as an instrument. And we built a consortium for that, and again, I would like to acknowledge who made that available for us and the consortium there. And of course, the last partner is the COMET itself, and I would like to thank the COMET really for its cooperation here. It's amazing how this COMET cooperated for us, not only in enabling it to be where we are now, but also, as you will see, in being entirely different from what we expected it should be. And that's really why we consider that this mission is fundamentally a success already. And to me, a very good scientific success is the point where we are, that what we discover essentially show that the question that we asked were not the right ones. And we are really building a new paradigm now, out of which the understanding of the solar system evolution, formation evolution really takes place. And I will just outline a few of that here. And of course, it's obvious that what we have been doing since months, it's not very much really. We arrived there in August essentially, so what we have found on Rosetta things months plus the November things has a lot, because again, it's very different from what we expected. Everyone knows that the shape is different, but more than that as well, see. And it was obvious that if we really want now to discriminate between the different options that we have here, we really dramatically need Philae to wake up to complete this mission. And the frustration we had, although of course we had a lot of things, the frustration we had after November, when we landed in this very peculiar pattern we had, is now really being exchanged, and new excitement, and again, the dream really that we had put together there is still there now, because the fact that not only Philae wake up, that it gives signal of this wake up is fundamental now, because it's opened new excitation for us to really complete the mission and possibly go beyond the expectation. What has been these 2 decades of space exploration is that really we discovered that planetary worlds, including the Earth, is much more diverse than what we could have expected. Planets is really not a single body just orbiting the sun, and just the distance between the planet and the sun would give you the rationale why we are so diverse here. Mars is different from the Earth, from Venus, whatever. And when you think of that, although we come from the same collapsing clouds, the drivers of planetary evolution is much more complex and much more fascinating than we expected. And the reason why the Earth is really entirely new now, entirely developed in a different pattern. And on top of that, you have the fact that 20 years ago, when we started that, we didn't know that exoplanets would be discovered and understood as they are now. And again, if you just want to have one word summarizing that, we would never have anticipated that the diversity of planets will also scope the diversity of exoplanets and of solar system and stellar system. There is not a single, at the same time the Earth appears so diverse within the solar system, our own solar system appears so diverse within the entire stellar system, more than 2,000 now we have, that we observe. And so of course the question is, how is that possible? How are the processes that lead to where we are now be understood? And the question of course that goes with that is what we have here on the Earth, and of course what we have harbored life, specific to our system or generic in the universe? And that's totally renewed as an address now. And Rosetta is in the core of that, because now we have to use Rosetta data to answer that question. Is what we see here unique or generic? And that's not trivial at all. So of course we had a dream to do so, because Rosetta was a mixture of in situ measurement over there, remote instrument and landed experiment. And so we had to land. And as you know, it was a dream up to November 12th. And that became reality just the day after. Okay, we had to wait another couple of hours, a little more than that, to make it happen, but it happened finally. And that was absolutely amazing, that for the first time, we put a 20 years old system on a 4.6 billion years system, that the oldest system ever conceived in our solar system. And this junction is really for the future. And we are very proud of having been able to do so in this fantastic image that came the 13th in the morning at 8 a.m. Of course, we know that the altitude is a little different from what we expected. We slept a little bit, so we have an odd altitude, and I will say, and this in the middle here is a fantastic image taken during the descent, but we knew it only afterwards by the Osiris. And so when I put that together, I said really the comet cooperated, because it was not obvious that when we bounced, we would not bounce with a velocity higher than the escape velocity, which is very low, as you know, 0.8 meters per second. And so while we saw after touchdown, a few minutes afterward, that we are still moving, or again moving, the question, of course, for us was whether or not we would be left over in the solar system back to where we were before, or whether we rebound on the comet itself. And actually, the second is the true, although we have not managed to understand exactly the system that really allowed that, but we are there. And actually, this gave us an add-on science by the bouncing itself, because not only we have the physical property of the bouncing that made the bouncing possible, but because we went from one place to the next by almost a kilometer, we have been able to monitor the system and hope, really, as it was a dream 25 years ago, to be from one place to the next, and we did that. And there is a lot of information that we got from that here. So it's an odd altitude, but it's highly shadowed and terribly exciting, and I will now focus on that. Highly shadowed. We have this cliff here among that we suddenly observed when just extending the dynamics of one of the camera, of the Shiva camera, and this cliff, and I love these images because it tells you that it's backlit, the sun is on the other side, and of course, because of that, we would never know whether we would be capable of waking again because the temperature was so low. We realized that although we have not entirely the recall, we are convinced that we went to a temperature lower than minus 150 degrees C. We qualified our system to that low temperature. It wasn't obvious that finally the system would survive. What happened last weekend is that actually our system survived and we are in very good health, although we went to down temperature minus 150, systems and instruments. We don't know for all the instruments, we'll know soon, we hope, but obviously, although we were in shadow, we survived, and that's really amazingly fantastic. But of course, there is a bonus there and a plus, and if some of you remember, as soon as we saw that, I called this cliff the perihelion cliff, because I said, well, normally, in the configuration that we hoped to be just landed where we wanted to be landed, we should have been dead by the end of March, because the temperature would rise to such a level that we would be dead by too high a temperature. Our system does not survive, the temperature goes over plus 40 degrees C typically, and that would have been achieved by the end of March according to the model we had. Thanks to that, we're in a shadow with all the risk associated with that, but we have the capability now to wake up and possibly have a very long-term activity, and that's really where we are now. It was obvious we would be there, we are there now. We've got, as you saw, some still fine-tuning to make. I'm convinced we'll do that. So perihelion cliff means essentially that now we are in a position not only to wake up, but to resume science to an extent that might go beyond our expectation, and I will give you 2 or 3 directions in which we would like to go. What is important in this picture is that really when you see this material, and again, never anyone was able to observe a comet within that sort of distances, a few tens of centimeters. We'll go back to that, but we already analyzed that and told the story. The story that this material is amazingly exciting because we are at hand, within distance of our lander, exactly the material that we would have dreamed to be able to analyze. Why? Because this material is really made of the pristine pebbles out of which the entire far solar system built, and we know that this material has really the record of the reason why we're here, probably. So that's really the growl we have here that goes. And for you to realize how we do that things now, we try to understand the reason why diversity went in 2 directions. What are the processes which model the solar system, and are these processes again generic or specific to our solar system? And when I say so processes, I will go back to that, it's essentially dynamic things, collision, interaction. And the word here of important is that, of course, the processes are very generic. The same interaction everywhere in the world, everywhere in the universe, the same interaction, the same collisions. that each of them can take a very specific form. And the variety of form it can take is such that it is the result of this variety of form that end to a variety of evolutionary pathways. And the question is, what is the probability that other systems might have gone through different pathways? And you will see it's not trivial. The second question, of course, is not only the process, but now the ingredients. Is the material formed during this collapse itself very generic or very specific to us? And that's something that we would like to know and that Rosetta will tell us, because we know that processes and ingredients are the two mothers out of which we are here. And the very good thing that Rosetta told her that indeed, analyzing the surface of the comet as it is now, we have access to that because the surface still records the very early processes and still has the very early material trapped in that we can analyze. And one of the reasons why Philae has to wake up now and analyze that, we have that in hand. One is this, you know now that this comet has a very specific double-shaped form. Actually, when you look at the, I don't have the picture here, but you all remember that, the very early Halley encounters in 86 comet, it also has some sort of double thing. So we should have already conceived that it's not only a potato shape, that there might be that. The question is, one of the questions is that the result of a collision that two bodies make only one? And is that the case, at which state this collision took place, what is the relative velocity? And do that sort of collisions really model the evolution afterwards? And how to know that? That's one possibility. The other, of course, is that just the opposite, that we have a single body which is now separating into two. And among the teams and among the time, the two models are still there. We have not yet finished understanding really how this comet formed. That we know that here there is something absolutely fundamental, which has to do with the first tens, maybe hundreds of millions of evolution of the solar system to understand how such bodies may have formed. We know that it's so fluffy that if the collision was to happen too rapid, of course everything would have exploded and we would not be here. So the question whether or not the two are correct is something fundamental. I will go back to that in a second. Ingredients now. What is this comet made of? And remember that in the early times, early being 2 or 3 decades ago, it's not that far away, we considered that the model that Weevil invented, that the icy comet would be made essentially of ice, having trapped grains and molecules. Even myself, I wrote that many times. We know that it's wrong. Comets are probably not that sort of thing. It's not icy body made of 80% of ice having trapped things. It's much more complex than that. And I have just added these pictures here because Mark a while ago showed them, and there is something here that might be misleading if you've got to understand. If I go very rapidly to this absolutely splendid picture that Osiris made over the last months, you have a lot of structures. First of all, these structures are not impact craters. They result from outgassing essentially, and we can elaborate on that. But more importantly, you have a lot of contrast, bright and dark. And when you see that this, for example, and I saw what Mark showed, this cartoon with people skiing there, it's a good cartoon, but it's a very wrong cartoon. What is bright here is essentially very, very dark. It's just by extending the dynamics of the images that you can make things appearing bright. The brightest places here are much darker than the darker place under the moon, 3 times darker. The albedo, as we say, the amount of reflected light is less than 5%. So every part of the comet is very, very dark, including this one. This is not ice. And this is with grains. And these grains, the dust, as we say, is essentially an organic matter. It's an organic matter. Essentially, CHO and N are the constituent of these grains. Why is that so important? First of all, it's entirely covered by that. And of course, when we saw that at the very beginning, it was last August and September, we said, okay, but that's maybe a result of the outgassing. We have a lot of ice below that, and at the surface, there is some sort of selection, and we enrich in grains. Probably it's true, we have enriched a little bit in that. But the fact that there is not a single spot of ice at the surface, including the places with fracture that in which we go deep inside, tell you something much more important. That it's not, the ice is not the cement out of which this body grew. Of course, you realize that it's very important because that tells something fundamental on the way the early solar system evolved. These grains, and I think I have a few things saying that here, these grains, don't read that. these grains are really the core, the material that cemented the entire body. Why is that so important? Is that these grains have been formed not recently. They have been formed while the early solar system cloud, pre-solar cloud, collapsed. It's a very specific chemistry. The chemistry during the collapse of a cloud, molecular cloud, as we say in astronomy, between grains, ions, cosmic ray, the source of energy, this makes complex molecules, but not only complex molecules, but complex molecules already aggregated into fluffy grains. And these fluffy grains might constitute 10, 20, 30, maybe % of the mass of this material. The comet is made of that. And this covers the entire surface. And this is shown now by many measurements that have been done from orbit. When you measure what you call the dust over ice ratio, you measure the amount of dust that goes out, you compute how much ice should be there to account for the water that we see, you make the ratio, and you have much more dust than ice. But what are the dust? The dust is essentially not silicate. These sort of grains are present, of course, but most of the dust is made of this carbon-rich material, which again have been made very early on. There are many, many measurements that go in that direction. As you will see, it's fundamental. Why? Because the question is whether this process, making these rich grains, are specific to our solar system or generic again. Of course, you have a lot of clouds collapsing because that's the source of the stars. Are we sure that every time you have a star forming in a collapsing cloud, the surrounding material will make that sort of very specific carbon-rich material that might afterwards have played a role in the emerging of life in the ocean themselves? We're not sure. It may be that in our solar system, the time at which the sun started as a star, the rotation of that with a very specific polarization of the UV light, whatever it is, might have really modified the chemistry itself, particularly with the chirality. That chirality is very important for the organic matter, giving rise to emergence of life. So all this is still there. We need to know that. And again, what is fundamental, that Rosetta has the possibility to give us clues, if not answering entirely the question here. So that's important because now we know that these materials, which are present there in the bulk of the comet, also at the surface, considering that, might have been these grains that implanted, cemented or feeding the early oceans in the planetary system, including at least, of course, the terrestrial oceans, might have been the source of the emergence of life. So we need to know that. It happened that, and this is fundamental also for you to realize that, for the moment we have analyzed this material in space, because Rosetta, for example, had the capability to sniff and to measure all the ions around. And there is a huge variety of molecules which have been detected here, showing that the carbon-rich material are much more complex than expected, with a lot of nitrogen, for example. We also had the possibility to measure that with a lander. You remember that when we land, this is the picture before and after, when you see on the right side the track of the 3 feet that really will up. Here, this the scale of the lander here. So that's what happened during the bouncing. And the bouncing actually lifted a big cloud of grains, and some of these grains entered the pipes of 2 instruments we have, Cossack and Ptolemy. It was planned already. We planned to measure by Cossack and Ptolemy after we touched down the material that would be lifted, possibly at the time Actually, it worked. Although we didn't know that the measurement would be done not in air, but in space. It's been made prior to be at rest. But that has been measured, and it's very interesting, and all these results will be published in the Science Review by a few weeks from now, with all the others papers that are being reviewed now. So something like a month from now, you will have all the results in details. But I can tell you that Cossack and Ptolemy have found a lot of carbon-rich material there, mixtures of aromatic and aliphatic. You will see that in a week or in some weeks. And combining that with Rosetta, we have, of course, a lot of possibility to understand what the material is. But, and this is fundamental also, for the moment, what has been measured essentially is sort of volatile that could be raised up to Rosetta, far away from the nucleus, and even by Cossack and Ptolemy, it's only the volatile compound part of these grains touching the pipes, which are typically at ambient temperature, that in volatiles and enter the instrument. For the moment, we still do not know what the refractory compound of this material is, and this is really the growth. So we want to have access to that. Of course, we didn't wake up, we would have done with all what we have now to try to go further. But now that we have a possibility to measure the composition, of course, of this material, we'll do that. The last sentence here, which is of course fundamental, is that we consider that if we wake up, and I will finish by that in a few seconds, these measurements are doable. With what we have acquired in November, we know that in a sense we were unlucky because when we drilled, at the direction in which we drilled, the surface was just a little further to the distance that we could reach with the SD2 as it was. We can reach typically 50 centimeters, it was maybe a little more than 60 centimeters. But by the same time, with the images that we got at the time and the processing that has been done since, we know exactly by which angle we should rotate, because the soil is not flat, it's like that. We know exactly by which angle we should rotate for the drill now to access the surface and even the subsurface, if it works fine. And that's not a big angle, it's something of 30 degrees plus or minus something. And we know exactly how and where to do it. So that's part of the game here, that if we wake up, and if we have the capability to go up to where we want to go, which is finally to have access to this material, we know how to get it, and we should do it. And so that's in the direction in which we will go. So, again, when you see this material, that's only 1 meter out of the lander as it is here, because you see down there one of the leg we have here. This material, which is very dark, which is flat, these are the carbon-rich material. They're everywhere, and we are at hand. That's where they are. We also have, when you see that the dry stuff, we have some ice also here. So we'll also have the capability to measure the isotopic ratios in the ices, to know what the ratios of H2O, CO2, that's all. We have very small grains. For example, here you have an enlargement of something that will be published actually only, so don't take pictures now. It will be published only a few weeks from now. You can take pictures. But again, that's not important. Just to tell you, whatever the scale, we see that even at a microscopic scale, we have this bulk carbon-rich material that would cement it also, probably icy grain there, and we have the capability now to access them and to analyze them here. So yes, the ground that we have is within distance, and that's where we'd like to go. So, collectively, we are really where we wanted to be. Collectively, we have to improve the connection between Philae and the lander. We are marginal in the duration of the connection, the link now. We are in a few tenths of seconds, minutes. We want to go to tenths of minutes. So the dream that we started a few decades ago, that happened last November as a reality, is being pursued. And as I would say, if it's a dream, I would prefer not to wake up. Thank you.
Thank you very much, Jean-Pierre. And I think with this, one thing is clear, science is anything else but boring. It's really exciting. If you ask the proper questions, there's enough excitement in doing it. Now we have still 10 minutes left for your questions. The microphone is over there. Please let us know your name and the affiliations or the media you're working for. And we have 10 minutes left for questions. Please give us a sign. Can you get a microphone? Thank you very much.
Sorry, Jonathan Amos, BBC. Can you just confirm that there was no contact last night? It's not unexpected, but if you could just confirm that. And also, just before Philae went into hibernation, you moved it, didn't you? Very, very slightly. You made it sort of stand up on its mechanism. Have you had any information at all back in the housekeeping data that it might have moved in the past 7 months?
Okay, first of all, yes, I confirm we didn't have any contact yesterday night, this morning, as expected. So this is for us a good news. So according to us, we were not supposed to have a contact. Regarding the movement at the end of the operation in November is correct. We lifted the lander a little bit, we rotated the lander in order to get the panel 1, which is a bigger panel, illuminated the most. I will say it's too early to assess for sure if the lander moved from its original altitude. It's really too early. Sorry.
Thank you very much, Barbara. Other questions?
Hello, Christian Gentot, Jacques Diziou, the service. You spoke about organic materials which were found. Do these materials include, I don't know the English term for acid aminé in French, aminé acids?
The question was, have we found any amino acid yet, right?
Amino acid.
So the answer is black and white. The answer is no. We haven't found them now. Two reasons for that. The way the things are analyzed are essentially not the global molecules for the moment. The instrument essentially see when you have a molecule, it breaks into parts, and we have analyzed the parts essentially now. So what I said is really where we are going to now. We want to analyze the bulk of this material, and that is for the future, hopefully in the coming weeks.
Thank you, Jean-Pierre. Other questions?
David Fossé from Ciel Espace. This is a question for Elsa Montano. I'm not sure to have understood your point about the stellar tracker. You have shown some pictures showing a lot of dust on the images. And is it because of the comet is more active than anticipated, or is it because the stellar tracker itself does not work as it should?
The star tracker behaves as designed. So the fact that there could be loss of track events in case of a dusty environment was anticipated, and the star tracker flies a sort of sunglasses to try to filter out as much as possible of these events. So the behavior we see is really due to the comet activity. So it's the reality of the environment we are flying in.
If I may, if no one is speaking, which is fine, I would like to answer the previous question, although the speaker has already left. The question was what are the information we have that we have not moved. Of course we don't know, but there is a very important information we have, which is that on the solar panels now, we have more than 25 watts, and that means that none of them, because we have really the sequence for all of them, none of them are covered neither by the organics nor the ice. And this is fundamental because it means that, and that was one of the fear we had, that by the time outgassing of the comet would essentially recondense on our solar panels material, which could have been possible, and that would of course have put some trouble in getting the sun transformed into electricity. The fact that we get essentially all the power we expected, nominally I would say, said that not only we have not moved, that the outgassing of the comet in the closed environment has not modified our own surface, and that's fundamental.
Thank you very much. More questions over there, please.
To Mr. Bibring, you said you were considering using the SD2 drill in the next weeks, months, but in November you used it at the last resort, at the very last time, because the lander was not outbound to the comet. Has it changed, and are you not afraid of moving the lander while using the drill?
So, whether we are afraid or not is not really an issue. Of course, we're always afraid, but again, the comet cooperates, and remember that. Now, as been said several times, we go to the less to the more risky things. We will not start rotating that, and when we will be rotating, we'll probably do it by step, and we have ways to verify after a given step rotation what the stability is, because we have ways to measure that and to observe it by imaging. So, of course, we'll not do that at once. I gave an idea of the sort of angle we'd like to rotate, 30 degrees, to give you also, I think it's not really complete round, it's a rather smooth thing that we have to do. But again, yeah, there is a risk associated with that. Not necessarily by the fact that we are not anchored, but just by the fact that we don't know exactly how we are sustained now. We have only 2 feet on the ground, I mean touching something, so the third point is probably the body itself. We don't know exactly, so rotation is always an issue. Although, when we rotate the body with respect to the feet, and of course the feet remain where they are. So, in principle, it's not risk associated. But on top of that, I would like to say the following. It may be that at the very first touchdown, as I said, we have we have had a cloud of material deposited here or there. And it may be that some of the ovens, because they were very small ovens, a few millimeters square, cubic, some of these might already have been filled with material. So we might have access to this material even without rotating. And one of the very first things we will do, actually, is to know whether or not that's the case, because we have an optical microscope here named Shiva M that we have not had the possibility to use yet because of obvious reasons in November. That's among the first things we will do, maybe 2 or 3 days after we will really start the scientific operation. Because if that's the case, it means that we already have this material in place to be analyzed by Ptolemy and Trezak by the stepwise heating instruments. Not to very high temperature because ovens are only allow a few hundred degrees, but that's sufficient already to do so. So even without rotating, we might be in a possibility in the coming weeks to analyze this so important material directly, without any movement.
Thank you very much, Jean-Pierre. Want to add something?
Just add that we did the first rotation in November, and we rotate of around 22 degrees. So it was successful. So we can hope that a new rotation will not endanger the lander.
Thank you very much. Another question? Yes, here in the first row.
Marianne Chandy from Espace and Expression. With this contact between Rosetta and Philae, do you think it will help you to find the exact position of Philae, or do we need the Osiris pictures to find it?
It will help to confirm, I think, the current location. But a definite answer would be a good image with a good resolution. That means an Osiris image made at 10 kilometers in altitude, for example. But of course, we will use the current data to try to find the current place at the best.
Thank you very much, Philippe. Now we come to the last question, if there is a last question.
Always the last question. You could already have the answer.
Exactly, so then we have already heard the last question. Ladies and gentlemen, thank you very much for being with us today, and be with us because the story continues. That's obvious. The comet, as Jean-Pierre explained, is very nicely cooperating, and I'm sure we can again expect the unexpected. All the news coming up, when the lander will wake up, and all these other things, you will find them on the blog, you will find them in social media, you will find them on the various web pages of all the partners in the mission. Thank you again for covering this mission. I think it's an exciting one and it will continue. Thank you very much.
Le risque majeur que l'on a, c'est pas qu'on va être soulevé par de la poussière qui d'un coup déciderait de partir d'en dessous de nous, parce qu'en dessous, c'est les endroits les plus froids. Au contraire, le risque que l'on a, c'est que le dégazage aux alentours de Philae vienne se recondenser chez nous, parce que nous, on est l'objet le plus froid de l'environnement, puisque par définition, on fabrique de l'ombre. Donc, non, le risque majeur, c'est pas... Il faut aussi bien se rendre compte que quand on met une image, quand on montre des images de dégazage, on étend la dynamique au maximum pour que vous voyez quelque chose. Il ne faut pas imaginer que c'est une soupière qui est à vive allure en train de sortir. La quantité de gaz qui sort est extraordinairement faible. On a des instruments tellement sensibles, comme le fameux capteur stellaire sur la sonde principale, que même quelques dizaines ou centaines de grains, vous les voyez tout de suite. Et comme le capteur solaire, il est limité à quelques milliers de points, ben, facilement on les a. Mais ça ne fait pas des... Ça fait pas des geysers du tout, c'est très continu, etc. Ça ne veut pas dire qu'il n'y a pas des geysers à la surface, mais on n'est pas dans ces endroits-là. Là, c'est des réflexions, ça passe pas à travers. Et donc, il faut être capable de bien connaître, mais c'est la même chose sur Mars, avec Mars 6, etc.
À 100 mètres près, vous savez où vous êtes.
On a mieux que ça.
Oui.
C'est quelques dizaines de mètres, oui. Mais à quelques dizaines de mètres, on est dans un endroit qui est très turbulent. Et donc, si tu veux vraiment bien prendre en compte la topographie locale pour sortir tout ce signal, il faut vraiment, voilà, il faut sortir avec la longueur d'onde de ce que tu veux voir, typiquement des mètres, quoi.
Turbulence de dégazage.
Non, la surface très chaotique, oui, il y a plein de gros blocs, etc. Tu as des falaises, des machins, bon. Donc, pour prendre en compte tout ça, il faut que tout ça je précise. Donc pour concert, c'est utile. Pour tout le reste, non.
Et donc pour la structure interne de la comète, parce que ça,
donc pour la structure interne.
C'est quand même super important.
Bien sûr, non mais bien sûr.
Ouais.
C'est ça que je dis. Donc pour la structure interne.
Sur cette manip.
Pour les autres, quelques dizaines de mètres, ça suffit amplement. On en sait suffisamment. On voulait le savoir avant parce que plus tôt tu le savais, mieux ça nous aurait aidé pour les liaisons. Parce qu'à ce moment-là, on sait exactement où on est. En reconstituant notre attitude, on aurait pu anticiper sur le moment où la liaison était plus favorable. Probablement. Mais bon, c'est pas. Donc maintenant qu'on a la liaison, ça nous aiderait de savoir où on est parce qu'on peut aller plus vite au réglage fin, si tu veux, parce qu'il faut qu'on arrive. On aimerait avoir 1 heure ou 2, si possible, de liaison. En principe, dans l'endroit où on est, il y a des configurations, on devrait avoir des liaisons qui durent plusieurs heures. Donc là, on est à la marge, simplement un lobe d'antenne, quoi. C'est à cause du fait que notre antenne, il est toujours sur ce panneau vertical, et qu'à cause de ça, si ton truc est très haut, tu as vite fait de le perdre. C'est d'ailleurs ce qui s'est passé pour le deuxième truc. Où en fait, on l'avait, mais on le perdait un petit peu, etc., parce qu'on était marginal. Mais on le voit non pas au négatif, mais au positif. C'est-à-dire que ça nous permet de mieux voir où on est, et donc d'orienter le Rosetta pour... À la limite, si on sait exactement où on est, on peut demander une configuration, et d'ailleurs l'ensemble des PI est d'accord sur Rosetta aussi, pour être dans une configuration où on ne bougera pas, on sera géostationnaire, cométo-stationnaire au-dessus du lander pendant 1 semaine ou 2 si on veut, ça ne coûte rien. Oui. Donc tout ça est possible, pendant lequel on peut vraiment faire une grande partie de ce qu'on veut faire.
Par exemple, ah non, ça dépend de l'éclairement.
Non, ça c'est le soleil, la comète elle tourne. Ça tu ne peux pas empêcher la comète de tourner, mais tu peux recharger les panneaux sur les batteries pour même travailler la nuit. Mais on n'a pas vraiment besoin parce qu'on a une grande partie des instruments qui peuvent quand même stocker, voilà. Dès qu'on a un petit peu d'énergie, il y a des choses qu'on peut faire. Toutes les mesures thermiques, tout ça peuvent être faites quasiment. Voilà. C'est clair?
C'est bien.
Super David, je t'en prie.
Une petite question, si vous avez encore une minute.
Oui, non, je t'en prie.
Concernant le filet, actuellement, si j'ai bien compris, c'est 2 plates par terre et 1 plate en l'air, avec une configuration à peu près à 45 degrés.
45, ça j'en sais rien.
Très incliné, on va dire.
Oui, c'est plus que 45.
Dans une infructuosité de rocher.
Dans un trou, hein.
Lorsqu'il sera passé au plus près du soleil, c'est-à-dire à partir du mois d'août, est-ce qu'on peut espérer que l'énergie soit suffisante pour risquer un petit bond et leur mettre un peu d'aplomb de façon à avoir éventuellement des panoramas un peu plus...
Non, on n'est pas armé pour faire des bonds, on n'a pas de système pour repartir.
Y compris avec le harpon qui n'a pas marché pour...
Non, mais le harpon tel qu'il est, si on s'en sert, ce ne sera pas pour repartir, ce sera au contraire pour s'ancrer plus et nous mettre dans une configuration plus horizontale, disons. Donc ça ne sera pas pour partir de cet endroit. Non, on n'a rien qui nous permette vraiment de le faire d'une manière programmée. Donc le but, c'est pas d'aller ailleurs maintenant, c'est de profiter de l'endroit où on est pour tirer le meilleur profit de l'endroit où on est, qui en soi est déjà génial, parce qu'on a un terrain qui est dans l'environnement très proche et passionnant. Donc on n'a pas besoin d'aller ailleurs pour tirer bénéfice de cette mission.
Et qui est à l'abri des grosses éruptions.
Et on est relativement à l'abri parce que c'est très chahuté comme paysage, donc on n'a pas de soleil en direct, ce qui nous a assez joué de tour jusqu'à maintenant. Donc au moins on va tenir avantage de ça maintenant.
Donc on a bon espoir maintenant d'avoir beaucoup plus de soleil, donc beaucoup plus d'énergie.
L'énergie n'est plus un problème. Pendant longtemps, le problème majeur était non pas l'énergie mais la température. On avait peur d'être trop froid pour pouvoir réveiller notre système. Maintenant, manifestement, la température a remonté. On a l'énergie qui va bien, donc on a tout ce qui va bien. La seule chose qui nous manque réellement, c'est la liaison avec la visibilité, donc de la liaison avec Rosetta. On ne peut vraiment bien travailler, c'est renvoyer des ordres et récupérer les données que si on a des liaisons qui se mesurent en dizaines de minutes. Et pour l'instant, on n'en est pas encore là. Mais ça, c'est un problème géométrique essentiellement. Donc il faut qu'on réalise réellement où on est. Et ça, on va le faire à l'échelle des jours qui viennent, on l'espère. Peut-être dès cette semaine. Et ensuite, donc, faire un réglage fin de la position de l'orbiteur par rapport à nous. Et dès que c'est bon, on démarre.
En espérant qu'il n'y aura pas trop de poussière pour cacher les panneaux solaires.
Mais ça aurait déjà eu lieu. Il y aura rien de plus dans la semaine qui vient. Le fait qu'on ait tellement d'énergie sur les panneaux solaires aujourd'hui montre qu'ils ne sont pas recouverts, ou très peu recouverts parce qu'en plus la structure des panneaux est telle que s'il y avait des ombres portées, ça mettrait tout à zéro. Donc ça, c'est une très bonne nouvelle, au contraire. Voilà.
Et donc on peut espérer un Philae en bonne forme jusqu'au moins 2 mois après le mois d'août.
En tout cas, on travaille pour. Voilà.
Vous avez parlé de rêve tout à l'heure.
Voilà, absolument. Non, mais c'est ça l'idée. Voilà, merci.
Merci beaucoup.
Je vous en prie. Au revoir.
Have a big picture, and the only way is to get
Great. It was very interesting. Thank you so much and good luck. Thank you. Thank you.
Ça m'intéresse.